So because so many people are out for the AP World field trip, I decided to just record the notes, and I am posting them on Google Classroom. So you'll take the notes just as if you were sitting in class, and then you'll be prepared for the practice stuff. As a reminder, I'm not going to be here on Thursday and Friday, so I'm leaving you with some practice activities for this set of notes. So it would be helpful to you if you finish these notes first. Okay, so in our journal, we need to define, and I have this on page 69, or I realized I skipped a number, so you might have this on page 68. We need to define what is an ionic compound. What is it? So what is an ionic compound? An ionic compound, unlike a covalent compound, forms between cations and anions. And traditionally, cations are metals and anions are non-metals. As a reminder, cations are ions that form a positive charge because they tend to lose electrons. So these guys lose electrons and then they take on a positive charge. Anions form a negative charge because they gain electrons. So in an ionic compound, we have metals bonding with nonmetals. In covalent compounds, we had only nonmetals bonding together. So if you're looking at a list of compounds and you're trying to figure out which ones are ionic and which ones are covalent, well, if you have metals present, then it is definitely not covalent. It would fall into the ionic compound category. And as a reminder, where you find your metals, on your periodic table, there's kind of that like region where there's a stair step that happens right around in here. Everything to the left of that is considered a metal. So that's what you're looking for. Ionic compounds do not share. They don't share electrons the way covalent compounds did. They completely give or gain electrons. So cations give up their electrons, anions gain electrons. There's no sharing involved. One person completely takes the electrons from the other atom. So that leads us into what are some of the basic properties of ionic compounds. Because of the giving and gaining of their electrons, they form very strong attractions to each other, because we got something that's positive being attracted to something that's negative. Because of that, since they're so strong, they have really high melting and boiling points. It takes a lot of energy to break the attractions. So that's why it takes a lot of energy to melt or boil something that is an ionic compound. They're also very conductive when they're dissolved in water, because they produce ions. And if there's ions present, then electricity can travel through that water. This is the reason why your toaster has a warning label on it that says it is not recommended to take this thing into the shower, because the water that's coming out of your tap would have ions in it, and if there's ions present, then electricity can travel through that water. So the next thing we need to talk about are Lewis structures. And how do you draw Lewis structures for ionic compounds? Because we did lots of practice with covalent compounds and showing how the electrons are shared between two atoms. But what happens when you have two atoms that one of them completely removes the electrons from the other? So for example, if I've got sodium and it is going to react with chlorine, what you have to do is think of how many valence electrons does sodium have. Sodium is in group 1 on the periodic table, so that means it has 1 valence electron. So I'm going to give it its 1 dot. Chlorine is in group 17, and so it has 7 valence electrons. So we get 7 dots. So everything is attempting to obtain a noble gas configuration, which means we want full valence shells. So sodium has one valence electron. Now that doesn't mean sodium only has one electron. It just means the outermost electron, there's only one of them. Remember, there's a full valence shell underneath this one valence electron. Chlorine has 7 valence electrons. So sodium is more likely to give away this one valence electron than it would be to try and gain 7 more to have 8 in this particular energy level, because giving this one away still gives it a full valence shell. It's just kind of like hidden underneath. And then chlorine is more likely to gain 1 electron instead of trying to give 7 away, and so that's what they do. Sodium gladly gives chlorine that 1 electron. So we can kind of represent this like a chemical reaction. This sodium gives chlorine its 1 electron. Sodium's happy because it shrinks down to its valence shell underneath. Chlorine's happy because it now has a full valence shell. And so if we write these guys as ions, or with their charges, the charge that sodium now has because it lost 1 electron is a +1. The charge that chlorine now has because it gained 1 electron is -1. And if we go one step further to show these things in a chemical formula, the ratio that they have to each other in order for everyone to be satisfied in this relationship is 1 sodium to 1 chlorine. And so that's what the subscripts tell us. So we would say Na1 and Cl1. So that is the chemical formula when sodium and chlorine form a bond. Let's do another one. What if we have magnesium and fluorine forming a bond? Magnesium's in group 2, so it has 2 valence electrons. Fluorine is in group 17, just like chlorine, so it has 7. Magnesium is more likely to try and give away these 2 valence electrons than it would be to gain 6 more. Fluorine is happy to accept electrons because it only needs 1 more. So if magnesium gives this fluorine 1 of its electrons, that fluorine atom is now satisfied, but magnesium hasn't quite satisfied its desire to give away 2 electrons. So if we bring in another fluorine atom, it can accept that second electron, and now magnesium has successfully given away 2 electrons. These 2 fluorines are happy because they now both have 8. And so if we write them as what's left after this transfer of electrons has occurred, magnesium takes on a charge of Mg2+ because it gave away 2 electrons. And then we have 2 fluorines that are both a -1. And so if we think about what's happening in terms of the ratio between the magnesium and the fluorines, in order for everybody to be happy, it took 1 magnesium and 2 fluorines. So the chemical equation would be Mg F2. That's what has to happen between those 2 guys. So there is a bit of a shortcut, and if you got my photocopied notes from when I was out, I did not include this shortcut in the notes, but I did talk about it. So the shortcut, if you kind of look at the periodic table, we already talked about a shortcut for determining valence electrons. Group 1 has 1 valence electron, group 2 has 2, group 13 has 3, 4, 5, 6, 7, and 8, with the exception of helium, which only has 2. So if we think about this in terms of what charge are these groups likely to take on because of their valence electrons, group 1 has 1 valence electron. Well, it is always going to give away that 1 valence electron so that it has a noble gas configuration. So group 1 is always going to be a +1 charge. Group 2 has 2 valence electrons, so it's always going to give those 2 away because it's easier to give away the 2 than it would be to gain 6. Group 13 has 3 valence electrons. It's easier to give 3 away than it would be to gain 5. Group 14 is a little weird because it's right in the middle, and so normally we just say that it's either going to be a +4 or a -4 because it can kind of go either way. Then we get over to group 15 with 5 valence electrons. If there are 5 valence electrons, then it's more likely that it's going to gain 3 electrons than it would be to give away its 5. So if it gains 3 electrons, it becomes a -3 charge. Group 16 would gain 2 electrons, and group 17 would gain 1, making it a -1 charge. So that's a bit of a shortcut that you can use to help you predict the ratio without actually having to draw these dots. Let me show you what I mean. So let's do the shortcut first, and then we'll draw the dots for the same example. So what if I want to know what happens between aluminum and oxygen? If I look for the charge that aluminum is going to take on, I find that it's in group 13, which means it's going to be a 3+. If I look for the charge that oxygen takes on, because it's in group 16, it's a 2-. It's going to gain 2 electrons. So then if I take these numbers right here can help me predict the ratio that aluminum and oxygen have to each other. And you just switch them, and that tells us the ratio. So when aluminum and oxygen get together, they have to get together in a 2 aluminums to 3 oxygens ratio. Let's do this with the dots to see if that actually works out. Here's aluminum with its 3 dots, and here's oxygen with its 6 dots. So this aluminum can give 2 electrons to that oxygen, but it still has 1 electron left. So we need another atom of oxygen with its 6 valence electrons. Aluminum can be happy now by giving that away, but now this oxygen atom is not satisfied. So if we bring in another aluminum, it can donate an electron to that oxygen, so now this oxygen is satisfied. But then we have an aluminum with 2 electrons remaining, so it looks like we're close to finishing here. So this aluminum can give those 2 electrons up, and we find that we end up with a 2 aluminums to 3 oxygen ratio. So if I were to write this as ions, I got 2 aluminums with a 3+ charge, and I got 3 oxygens with a 2- charge, because each of those oxygens picked up 2 electrons. So they each have a 2- charge. And then if I think about the ratio, 2 aluminums for 3 oxygens, I end up with Al2O3. So that is the formula. So there are several questions like this on the UT Quest. I say several, there's, I don't know, probably 5 or so, where it's the dots, like transferring of the dots. And the key there is just making sure that you look at all your answer choices and make sure that they're representing, like you wouldn't want magnesium with only 1 dot because it has 2 valence electrons. So the right answer has to have a magnesium in it that has 2 dots, 2 electrons. So just work through this process and find the one that is correct, and those should be fairly easy. Well, the other component to what we have to do is, how do you look at a formula, or how do you look at a name and do the other half of that? And a big thing is that you cannot apply covalent naming rules to naming ionic compounds. We do not ever use prefixes for covalent compound, or for ionic compounds. So going from the formula to the name, for the most part, is pretty straightforward. There are some like little tricky things, and we'll try and go through those. So the very first thing you have to do is you write the name of the first element. If it's a transition metal, if it's tin or lead, then you have to include a Roman numeral. So we'll do some of those in a minute. If it doesn't fall into this category, then you just write the name of the first element, and that's it. So for this guy, the name of the first element is sodium. So the name of the first element is sodium. You don't have to do anything, you don't have to change anything, no prefixes. You just write down the first element. And since sodium doesn't fall into this transition metal, tin, or lead category, we don't have to do anything with a Roman numeral. So the next thing you do is you write the name of the second element with an "ide" as the ending. If it is a polyatomic ion, you don't change the ending to "ide." Cl is not one of your polyatomic ions, and the way you know it's not polyatomic is because it's only 1 atom. Polyatomic looks something like this, where you have like a group of 1 or 2 or more atoms. So like SO4, and you should be working on memorizing those. So Cl is not a polyatomic, so we just name it with an "ide" as its end. So it is chloride. And that's it. So this one, we write the name of the first element, magnesium. Magnesium does not fall in the transition metal category, so it does not need a Roman numeral. And then we write the name of the second element. N does not fall in the polyatomic ion category, so we just write its name with "ide" as the end. Magnesium nitride. Here we have Fe, which is called iron. We write the name of the first element. Iron does fall in the transition metal category, so we have to think about these Roman numerals. I should say Roman, not Romal. Roman numerals. And so where the Roman numeral goes, it always goes in parentheses right after the name of the first element. So let's just leave a space for it and we'll come back to it. So we got iron. We know we need a Roman numeral because iron is part of the transition metals. And then we have this oxygen, which is not a polyatomic ion, so we just call it what it is with an IDE at the end. So this would be oxide. Okay, so now going back to the Roman numeral. If you think about how I showed you how we can take the charges and determine what the ratios should be, we do that like crisscross thing. I'm going to reverse that process. This 2 is here as a subscript on the iron because it came from up here on this oxygen. The oxygen was a 2 minus. And I can verify that by checking the periodic table, that oxygen is in fact a 2 minus because it's in group 16. This 3 is here because it was the charge on this iron. It was a 3 plus. Let me pause here to remind you that the cation always goes first, so whatever the first element is always going to be positive. The anion always goes second, so whatever the second element is always going to be negative. So I don't need a Roman numeral for oxygen because I know that it can only be a 2 minus. That's what the periodic table tells me. It has 6 valence electrons. It's going to gain 2. That's the only possibility. But I have never talked to you about a shortcut for the transition metals. And the reason is there isn't one. The reason we can't use a shortcut for these guys is because there's more than one possibility for the different charges that these guys can have. And you don't have to know the science behind why they can be more than one particular charge. You just have to know that they can be. So for example, iron can be either a +2 or a +3, and that's where the Roman numeral comes in. We have to, in the name, give the Roman numeral so that we know, is it a +2 or is it a +3? And so by unscrambling the crisscross or the swap and drop, I find that it's a +3. So all you have to put in the parentheses for the Roman numeral is the Roman numeral 3. So that takes care of that one. Here we have calcium sulfate. Calcium is not a transition metal, so it doesn't require a Roman numeral. And this right here is a polyatomic ion. The reason I know it's a polyatomic ion is because after I wrote my first element, the stuff that's left is more than just one element. I have an S and I have an O. So that falls into that polyatomic ion category. And you are supposed to have been working on memorizing these, and so when you look this guy up, you find that the name of the cluster of elements that's S to 4 oxygens is called sulfate. And so up here in the rule it says if it's polyatomic ion, we don't change the ending, so you just call it what it is. So that is calcium sulfate. So this one, we name our first element, and that guy is barium. Barium does not fall in the transition metals. It's in group 2, so we don't have to use a Roman numeral. And then I know that this is a polyatomic ion because after I looked at barium, there's more than just one element left. There's 2. There's phosphorus and oxygen. And so I find that the name of that is called phosphate. And that is it. And then this last one, this one's a little tricky. so we'll try and go slow through it. So Pb is called lead. Lead is one of these that requires a Roman numeral, so I'll put a parenthesis there, and we'll come back to that. And then this SO3 stuff, the second part of this compound, that is a polyatomic ion. I look that up and I find that this is called sulfite. Sulfite, not sulfate. It's got one less oxygen than sulfate, so it's sulfite. And so now I'm stuck with the task of figuring out what is the Roman numeral supposed to be. Please know that this 3 is part of the polyatomic ion. It is not there because it was crossed down from the lead. It belongs to the oxygen and the oxygen alone. If it helps, you can always put your polyatomic ions in parentheses, and whatever's on the outside of that parenthesis is what was crossed down from the other atom. So since there's nothing there, that's an assumed 1, right? And there's nothing here, which makes this an assumed 1. But you have to know that all these numbers tell us are the ratios. So what this is telling me is this is a 1-to-1 ratio between lead and sulfite. I don't know the charge of lead, but I do know the charge of sulfite from memory to be 2-. So if the quantity of atoms is a 1-to-1 ratio, the charges must also be in a 1-to-1 ratio. So if this charge is a 2-, then that means this one must be a 2+ in order for those to be in a 1-to-1 ratio. So the Roman numeral that I would use would be a 2. That one's a little tricky, and I will try and not give you a ton of those. But like there is a rule that says you reduce if possible, and we'll see that down here. So this is kind of like working backwards from that reduction. Okay, what if you're going the other direction? So the first thing you have to do is determine the charge and symbol of the cation. And as a reminder, this is always the first element. The cation is always written first. The anion is always the second element, or elements, I guess, if it's a polyatomic ion. So if I find the symbol of beryllium to be Be, and then I look on the periodic table, beryllium's in group 2, which means it's a 2+. I find the symbol of fluorine. Since this ends in ide, I know that it's fluorine from the periodic table, the element. I find F, and it's in group 17, so it's a 1-. Take those numbers and you crisscross them and reduce if possible. So this tells me the ratio of Be to F must be a 1 beryllium for every 2 fluorides. Aluminum has a symbol of Al. It's in group 13, so it's a 3+. Sulfide, if it ends in IDE, it comes from the periodic table. The one exception to that is cyanide. That is the only polyatomic ion that ends in IDE. All of the others end in some other ending. So sulfide is just sulfur. It's also in group 16. So it's a 2-. So when I take those numbers and swap and drop them, I'm not adding or subtracting or anything like that. I'm just trading and crossing them down. I get Al2S3. Cobalt is CO. There's a Roman numeral there which tells me the charge on the cobalt, 3+. Oxide is just oxygen. From the periodic table, it's a 2-. Take those numbers, crisscross applesauce. C(o), 2, O, 3. It's the compound. Then copper 1 nitrate, Cu. That Roman numeral 1 tells me this is a +1. Nitrate, since it ends in ATE. That's a good clue that you need to check your periodic table or your polyatomic ions list. And you find that nitrate is NO3 with a 1- charge. When you take those ones and you swap and drop them down, you end up with a 1-to-1 ratio between Cu and NO3. Ammonium phosphate. Ammonium is the only positively charged polyatomic ion, so don't look to the periodic table to find ammonium. It's NH4 plus. Phosphate is PO4 3-. I'm going to take those numbers and swap them, and I'm going to find here something interesting happens. This 3 is going to end up right next to this 4. You don't do any addition, you don't do any multiplication. When you have two subscripts that end up side by side like that, you have to put your polyatomic ion in parentheses. So I'm going to put the NH4 because it always has to be NH4. It can never be NH anything else. It always has to say NH4 if we're talking about ammonium. So I put it in parentheses, and then I put the 3 on the outside of the parentheses. So the parentheses separates the 4 and the 3. And then the PO4 ended up with a 1 out here, so I didn't have to put a parentheses around my PO4. And the last one, chromium 2 sulfate. Chromium is Cr. That 2 tells me this is a 2+. Sulfate tells me to look at my poly list to find this is SO4 2-. I'm going to take those numbers and swap and drop them. However, remember that if you can reduce, because we're looking for a ratio of atoms, the ratio of whole number atoms, these can reduce by a factor of 2, which means this is a 1-to-1 ratio. So we would get CrSO4 because they exist in a 1-to-1 ratio. This guy gives up 2 electrons, this guy accepts those 2 electrons, and so you only need 1 atom of chromium and 1 polyatomic ion of sulfate to make everybody happy here. Okay, so if you have questions over the next 2 days, feel free to pop in and see Miss Lava or potentially Coach K, and I will see you guys when we get back from break.